Thank you very much. I'd like to thank the organizers for inviting me. It's a great, does that sound okay? Okay. It's a great pleasure to be here, see everybody. Pleasure is slightly mitigated by the fact that I have a cold, which I got from the cab driver. It took me from the airport. Anyway, I'm going to be talking about a fairly simple example of a spectrum triple. I'm calling these Euler triples. And especially there are some aspects of them that I find quite puzzling personally and a little bit intriguing that has a little bit to do with dynamics. So just the construction starts with gram differential on Rn, the gram operator. So D, and then D plus its adjoint defines a self-adjoint elliptic operator in Rn. So what I want to do, this is of course not Fredholm, it's kind of locally Fredholm, but I want to perturb it by adding a potential. So I'm going to let omega be the form dx squared, so some xi dxi divided by 2. And the so-called Euler operator, I use this term because I think mainly it was called this in a paper of Nigel's. And then a few other people have also referred to it by the Euler operator. So I perturb the gram operator by this external multiplication by the form omega plus its adjoint. And what you get then is an operator which is elliptic in a certain sense. It's so it's self-adjoint, but it has discrete spectrum. And the singular values, the dimension of this kind of non-commutative geometry is 2n. So the singular values are approximately given by n to the 1 over k to the 1 over 2n. Okay, okay, so this is a very beautiful example of an operator. It commutes mod bounded operators or elements of a fairly large algebra. This is sort of a universal algebra for which the commutators are bounded. Like, in a sense, I take, just to write this down. So if you take the algebra of smooth functions in Rn, all of which derivatives are bounded, okay, then this is a this is dense. In this Heath algebra of uniformly continuous functions on Rn, the bounded uniformly continuous functions on Rn. Okay. Okay, so if you take the commutator of one of these functions with d, of course the function commutes with this term, and the commutator with this is essentially the derivative of the function. That's bounded. And I have a group acting here as well, which is Rn, acting by translation, but I give it the discrete topology. It's a bit unusual, but it seems to match what we want. If you take translation by an element t in Rn, it commutes with this part, and the commutator with this part is essentially t, so it's bounded as well. This is almost the Fourier transform of this, but this is not quite true. I don't actually know the exact state of affairs. I'm not sure how to describe the Fourier dual of this. close to this, but it's something slightly larger. But I'm just going to work with this for the moment. Now, this algebra has a lot of, it sort of contains lots of interesting subalgebras that come from dynamics. So, oh, but actually, before I do that, maybe I'll just, for n equals 1, you can describe this operator in a really nice way. It's a 2 by 2 matrix with x plus b dx and x minus b dx along the diagonal. I mean, in the off diagonal entries. Okay, and then actually d squared is 2 copies of the harmonic oscillator, plus or minus 1. Okay, I'll be talking a lot about dimension 1 today, because the interest in this operator is really in dynamics, and in dynamics you don't care so much about very general sort of groups and things. I mean, the group of real numbers is already quite interesting. So, subalgebras from dynamics. So of course, yeah, if you have any subalgebra of this algebra, the Euler triple restricts to a spectral triple over the subalgebra. And so you get spectral triples over all of these kinds of examples. So probably the simplest example of kind of immediate interest is if you take a pair of lattices, Rn, and then you form the kind of generalized rotation algebra modeled by the one lattice and let the other lattice act. So of course, in dimension 1, you could, when n equals 1, you could take one lattice to be the integers and the other lattice to be, I've been using the Planck constant instead of theta. I just can't break the habit now. So this gives you an irrational rotation algebra, dimension 1. So this fits in a pretty obvious way into this this algebra. The functions on Rn mod gamma 1 list 2 gamma 1 periodic functions on Rn, and they are uniformly continuous because this is compact. And gamma 2 fits inside Rn with the discrete topology. And of course, this would not be true if we gave it the non-discrete topology. All right, so that's a kind of a, so you in particular get a spectral triple over these types of algebras, but these are not actually the most interesting ones. So the first way of making this more interesting is to take not that example, but this one. If you take the tensor product of continuous functions on Rn mod gamma 1 cross gamma 1, with the one that you get from doing it kind of the other way around, C of Rn mod gamma 2 cross product gamma 1, this also fits inside this algebra in a canonical way by doing the same thing we did before with each factor and then just multiplying them. So this makes sense because if you take a gamma 1 periodic function on Rn, it will commute with gamma 1, right? And the action of gamma 1 commutes with gamma. Oh, sorry, yeah, my apologies. And then similarly, this commutes with this, and these two obviously commute, so you get 2 commuting representations into this algebra. And the kind of functions that you get by multiplying a function here and a gamma 1 periodic function and a gamma 2 periodic function, these are no longer periodic functions, somewhat more interesting. And I like the fact that there's a tensor product here as well, because part of the my original goal in looking at this operator was to construct a KK duality using it. And this KK duality, which I'm still working on, but I'm not going to talk about today, has to do with transverse groupoids. So let me give you another example closely related to that one, which involves transverse groupoids in a more explicit way. So if you just take two transverse subgroups, maybe I'll say subtor, connected subgroups inside the n-torus. So just transverse subgroups in the sense of differential topology. Usually dense, so well, there's two of these, but they should be transverse. I don't want to mess up the picture. So it should probably be dense. Okay. Then what you can do is take their intersection. And then this will be a dense countable subgroup. Of either of them, L. And it lifts to a countable dense subgroup of Rn. Okay, so it fits inside this. And then we get an inclusion of this cross product into our algebra. Once again. And incidentally, so in terms of the connection to duality, this is actually Morita equivalent. To the cross product, to the tensor product of these two flows tensored together. So you see a kind of similar phenomenon over there. This will give a Morita equivalent spectral triple over this as well. Okay. But what I became quite interested in, though, is certain sort of technical aspects of these spectral triples. So I'm not going to be talking too much about K-homology or anything. Well, actually, before I go on, let me just mention something else. I recently learned a new word. It's the word ambit. So it took me a surprisingly long time to find this out. Google really didn't serve me well. I'm not sure why. This is a commutative C-star algebra, so it has a Gelfand spectrum. It's continuous functions in some compact space. And the compact space is called the Samuel compactification. So this is Samuel compactification. And this is actually quite, well, what I want to say about this, it's important in minimal dynamics, actually. It serves as a kind of a universal object, in a sense, for ambits. So given a given an action or n on X compact, and X naught and X was a dense orbit, there exists a unique map, unique Rn map. And the semiotic application to X mapping 0 in Rn. Compactification, so it contains Rn to the point. This appears somehow in logic, but also shows that somehow this algebra is already known to have something to do with dynamics. Okay. And by the way, in terms of examples, I'm also quite interested in some examples of flows which are not on manifolds. So there are some spaces associated with tilenes, aperiodic tilenes, which also kind of fit into this, but I'm not going to get into it right now. Okay. So I should mention that Kahn, Moscovici, and Lesch studied the, I think they called these Heisenberg cycles or Heisenberg triples over the irrational rotation algebra, which, as I mentioned, fits into this. It's a subalgebra of this, and they proved a few things. Actually, so I realized this quite late in the game. Actually, it wasn't completely obvious to me, but somewhere in Kahn's book, it already appeared in Kahn's book. What he showed in modern sort of terminology is that, well, so if you have Kronecker flow along lines of slope, say h, and then if you take a, so you have this picture lattice, and then you've got these lines, and so if you take a pair of relatively prime integers, say, then you can construct a, well, I'm not going to draw it, but you can construct a compact transversal. It doesn't actually look very transversal. You can construct a compact transversal, let's call it L, to, or maybe call it T, to Kronecker flow, and that gives a strong rate equivalence between the irrational rotation algebra and the Kronecker flow C-square algebra, the cross product by R. But then you can also take another transversal, and you can sort of follow the one by the other. And this method gives you, for every element of GL2Z or something, it gives you an element finally projective module and an element of K-theory of irrational rotation algebra. These are very nice geometric K-theory classes. And what actually happens is that, well, Kahn is this proved one of the earliest instances of KK duality, which is a favorite subject of mine. And essentially what happens, what he proved is that the Poincare dual of one of these K-theory classes made from transversals is roughly given by the same construction. So it's the class of the spectral triple that I just kind of described. So, or a direct sum, sort of up to a kind of multiplicity. A little bit vague about that. You might have to take the direct sum of finitely many copies of this in some way. depending on the integer. And so Kahn observed, you have these interesting things that already appeared in Kahn's book, and he proved an index theorem for them as well. So I didn't really know about this at this point, but I thought, well, these are interesting examples of spectral triples. Why don't we compute their Turing characters and see what we get? So I gave this project to some students at UVic, one of whom is here, Nathaniel Butler and Tyler Schultz, and asked them to study the spectral triples of the irrational rotation algebra. And they proved a number of nice things. In the end, I'll just mention this. If you take one of these, so let me be kind of a little bit more precise. So if you take L2R twice, 2 copies of it, with the obvious representation of AH, and then D, this Euler operator, and you take its Turing character in the sense of Kahn and Moscovici, there's quite a cute answer. So now, in order to do this, so I'm fitting the irrational rotation algebra. I wrote it AH before, but I should really write H mod the integers. I mean, obviously this only depends on the class of H mod Z. But when you fit it into our universal C-star algebra, you have to actually pick a real number H. And the construction depends on the real number, not just its class mod Z. So you put this into bounded operators in L2 bar. Okay, and then you get a spectral triple. And so the interesting thing is that the nice thing is that the Turing character of this gadget is it's a mixed cyclic cocycle. In degree 0, it has standard trace on A theta. And then you have in dimension 2, you see H times tau 2, where tau 2 is this curvature cocycle of Kahn, 2 cocycle of Kahn. And so, but it's multiplied by this number H, so you pick up information about the lattice when you take the Turing character. I think it's kind of cute. And moreover, it follows from this formula and the local index theorem, but the pairing, I haven't really worked out a good notation for this thing. Maybe let me just temporarily call it DH. Denoting the spectral triple, or the class of the spectral triple. Anyway, it follows from this that if you pair the class of the spectral triple with the real field projection, which is one of these type of classes that comes from this construction, then you get the greatest integer less than H. Which is kind of interesting. You see these jumps as H moves. But Kahn talks about this in his book from many years ago. Okay. And okay, I should mention that more recently, so this aspects of this operator and the spectral triple that it makes, they do things slightly differently. They do things a little differently from what I'm doing, but it's certainly related. This is studied by Savin and Schroer. And they studied the local index formula for our end of these spectral triples, but they were not interested. They were interested more in sort of lattices and things like that, and groups. Not so much uniformly continuous functions. Okay, but one of the things that comes up is that if you want to apply the local index formula to these examples, then you need to know, well, you need to know some stuff, like the meromorphic continuation property, the meromorphic extension property. Okay, I mean, I think the sort of the local index theorem in noncommutative geometry is a little above my pay grade. I don't really know what the state of the art is, but I know very well the account of it due to Nigel. And the proof of Nigel relies really heavily on this property. So, which says, you know, you need something like this. F goes to the trace of A, B to the minus, well, 2S, I guess. So this is defined for real part of S bigger than N. And you need this to meromorphically extend to the complex plane. And of course, you would also ideally like to know something about the poles. And here A, well, A is some element of a priori. I mean, in the most kind of general setup, A would be an element of this algebra. And so I had no idea really how to prove this. So if back in these earlier papers of Kahn and of Moscovici and Lesch, for example, this is proved for like periodic functions, and it's relatively easy for those functions. I'll come back to that in a little bit. But here, I'm most interested in A equals F. Function, which is not periodic. And it was a real mystery to me how you could establish this meromorphic extension property. And this is what I'm going to talk about now. Made some very limited progress on this. But this is the, but what's happened seems to me kind of interesting. Okay, so maybe I should just mention, I mean, how do you, classically, how do you prove that zeta functions like this meromorphically extend? I mean, if D is something like an elliptic operator on a complex manifold, it has so the Heath kernel has sort of, well, so it's an integral operator with the kernel. Okay, so T of XY. And, it's one of the sort of fundamental results of this subject that the Heath kernel has an asymptotic expansion. And this was one of the things that Theo got quite excited about. It has the asymptotic expansion. I can't remember exactly, so something like this. Okay, and then so well, if you combine this asymptotic expansion with the Mellin transform, so the Mellin transform tells you that if you, for example, multiply function on the manifold by e to the minus 2s, this is equal to up to a constant, maybe. Okay, so it's f e to the minus 2d squared. Oops. Mellin transform gives you an expression like this, and then this is a smoothing operator. So its trace is the integral. It's integral along the diagonal. So you get an expression like this, and if you plug this asymptotic expansion into here, well, you see that you get a meromorphic function, and the poles are sort of at these. And at the poles, you get sort of these things. Well, they're going to depend on f. What these are going to be are distributions, and potentially quite interesting distributions that are worth studying. But in this setting, as far as I know, anyway, there's not any analog of this. There's not a direct analog of this argument. So it wasn't clear to me how to proceed. So as I said, I was working on this with these students, and these guys came up with something quite interesting. So this is, some of these computations appear in a paper by Butler, Emerson, and Schultz. And one of the first things they proved was, well, they don't know quite. We don't know whether. So this is n equals. I'm just going to be talking about n equals 1 from now on. We don't know whether this meromorphically extends. So then d squared is a harmonic oscillator. So we're looking at this kind of functional here. We want to meromorphically extend this from real part of s bigger than 1. So we don't know whether it meromorphically extends, but if it does, then it should have a pole at 1, and it should be the case that the limit as s goes to 1 to the positive side of s minus 1 trace f h to the minus s. This limit should exist. And so what they did was they show that by various, like some direct computation, slightly involved, but do it. So call it a proposition. So what they showed is that the limit as s goes to 1, s minus 1, trace f h to the minus s, exists if and only if another limit exists. So this limit is the limit, lambda goes to infinity. It's 1 over 2 square root of pi equals from 0 to 1 integral over r f of x t to the minus lambda e to the minus x squared dx dt exists. And if the limits exist, they are equal. And maybe more to the point, this happens if the limit as x goes to plus or minus infinity, 1 over x integral from 0 to x f of t dt exists. So you take these sort of averages of going in positive and negative direction, and if these limits both exist, then this limit exists as well, and then so does that. And in this case, the limit is the average of the two limits that happen here. We call these tau plus or minus f. Well, that's sort of good because it's sort of interesting because this happens for a lot in the context of ergodic flows by the Birkhoff-ergodic theorem. So, so if R acts by an ergodic flow, on a compact X, then for almost everywhere X and X naught, back to ambits again, then for almost everywhere X, this is these limits exist. So T goes to infinity 1 over T, integral from 0 to T, and not only does it exist, but it's equal to, so if mu is an invariant measure on X, these time averages converge to the integral of f. So in the context of ergodic flows, these functionals that appear in connection with these residues are actually given by integration of functions over the manifold. Okay. Okay, so sort of following the road from here, yeah. H, as in big H, or? Well, no, these only depend on f from the flow. F is a function on the manifold, and you restrict it to the orbit of x naught, so you get a function on R. And so then you can look at these, the zeta function. I mean, yeah, I guess so. The interesting thing about this theorem, of course, is you can kind of recover the invariant measure by just looking at a single orbit. So a single orbit for an ergodic flow carries a lot of geometric information. But the interesting thing is exactly that this, well, is that H is not here. I mean, this is a completely geometric thing. Has to do with dynamics, and this has to do with analysis. So. Okay, so kind of pursue this idea. We started to think about the following. Well, there might be a connection to what's called dynamical cohomology. So in dynamics, you often think about something called the cohomological equation. And so if R acts on X by flow, X is compact, and V is a generating vector field. You can ask the following question, or family of questions. So dynamical cohomology starts with this question. So if you can pose variance of this question for different assumptions about regularity and requirements about regularity, and this is regularity is quite a big issue in this whole conversation, but I'm not going to talk too much about it. Let's just say if F is smooth for a moment. Anyway, is VG equal to F, or does VG equal to F have a smooth solution G? So is that true for every F? And this is a kind of a hypoellipticity. This is sort of like hypoellipticity. So one abstraction, kind of an obvious abstraction. And the whole point is there are situations where there's more than the obvious abstraction. But the obvious abstraction is that, I mean, if the flow is sort of denoted alpha sub t, and if mu is an invariant measure, then this expression here, which a priori depends on t, is actually constant. And if you differentiate this, you deduce that the integral of v of f d mu is 0 for any f. Oh, maybe I should call this g, because so the mean is an abstraction to solving the cohomological equation. Okay. Now, if you go back, if you look at if you sort of solve the Heath equation and explicitly write out the corresponding integral formula for the zeta function, you get something like this. This is by Mailer's formula. It's called Mailer's formula, or it's a formula for the Heath kernel. Okay, so you have this. Now, the point is that if f is a bounded antiderivative, then you can use an integration by parts argument here. So this thing here is roughly t to the s minus 2 as t goes to 0. Right, so this is sort of analytic for s minus 1, real part of s minus 1 bigger than 0, so real part of s bigger than 1. But if f is equal to g prime, then you can use an integration by parts thing, and just integration by parts, and you get to this by an easy calculation is equal to this. You get a factor of square root of hyperbolic 10. Yep, otherwise you get essentially the same thing there. And now this is now roughly t to the s minus, 3 2s as t goes to 0. So this is analytic now for a real part of s bigger than a half. And so we've made progress. In this case, you can analytically extend from real part of s bigger than 1, real part of s bigger than 0. And so what you see now you see a meromorphic function. And then if you can keep doing this, then you can meromorphically extend to the whole complex plane, and you get one pole at s equals 1. And sort of the functional there is exactly the mean of f, the integral of f with respect to the invariant measure. If well, let me write that statement down properly. So that's the theorem. If a flow is cohomologically trivial, in the sense that the cohomological equation let me just the strongest possible hypothesis again, or the simple hypothesis on regularity. If it has a smooth solution for all f with zero mean, then trace the f h minus s meromorphically extends to C. It has a simple pole. That's equals 1, and the residue there. Is the integral of f with respect to the invariant measure. Okay. If there's an invariant measure for which this statement is true, then the zeta function meromorphically extends with a single pole. Yep. So this tells you that if f is zero mean, then it has an antiderivative under the flow, and then you can repeat this. So in this scenario, if you take a general f, you just subtract its mean, and that will have zero mean, and then you can plug it into this machinery, and you get this. So I'll just give you a quick example. Oh, well, just to show you that this is kind of cute. So if you look at Kronecker flow, along lines of slope alpha, where alpha is irrational. When is this flow cohomologically trivial in this sense? Well, actually, even before I do that, look at the usual flow on the circle. What about this one? Okay, well, this uses Fourier series. So if you want to figure out whether some function has a bounded antiderivative or a continuous antiderivative or something, write it in a Fourier series. This. And then, of course, differentiation on the circle just multiplies by 2 pi in. So if A0 is 0, and this works even for f continuous, then this gives you even a continuous antiderivative for any f with zero mean. And so you get meromorphic extensions of the zeta function for these examples. What's interesting about this, I think, perhaps, is that this statement, as I say, is true for even continuous functions. There's no smoothness or anything. So for Kronecker flow, if you want to do the analog of this, and these questions, these questions about dynamical cohomology, I've been learning about this. The main technique is Fourier analysis, so this is the sort of standard technique. If you were to look at Kronecker flow, Fourier series look like this. The vector field is sort of it's diagonal. It's multiplication by n plus alpha m in the nth coordinate. And so if the A00 term is 0, then you want to say, well, I can find an antiderivative by just dividing as before. So I'll let g of x, y be some if the mean is 0. And now I'm going to divide by 2 pi I n plus alpha m in the nth coordinate. Okay, so then this is going to be an antiderivative. But what's the problem with this argument? Well, the problem with this argument is that these terms can get very close to 0. Alpha is irrational, and so you've got a bit of a problem in general. But so this works for f smooth and alpha satisfying a Diophantine condition. So because the Diophantine condition says that this gets close to 0 only at a polynomial rate. That's what the Diophantine means. And if f is smooth, this decays faster than any polynomial. So this works in that case, but it's sort of well known in dynamics that you really need this hypothesis. So cohomological triviality really only happens, I mean, there are actually theorems about this. It only happens pretty much for linear flows on tori with Diophantine periods. Okay, so let me just finish by talking about what is happening recently in dynamics. There's an Italian named Giovanni Forni, and he's proved a whole bunch of things. There are other people, like names like Zorich appear here. Also, Forni has a student named Rodrigo Trevino that we're actually working with. And what he proved is that as I say, for other examples as well, but for horocycle flow, for instance, on a Riemann surface, there are infinitely many obstructions to solving the cohomological equation. Continue to call star, given by invariant distributions. And moreover, Forni shows that there are asymptotic expansions. This is kind of the climax of this talk. It's supposed to make you excited. So remember, I mentioned asymptotic expansions in the classical situation of elliptic operators, compact manifolds, that look like for ergodic time averages. Okay, it looked kind of like this. So first of all these terms. The first term is the mean of f multiplied by t, and then you have these different ones. Okay. And these are, so you have sort of 1 bigger than alpha 1, bigger than alpha 2, these are decreasing. You see, I mean, you know, the Birkhoff ergodic theorem says if you divide this by t, it should converge to this first term. So, because when you divide by t, all these other things go to 0. And so this implies the corresponding statement about the zeta function. This is just again for flows. Okay, so I'm lying slightly because the problem is Forney's work, this is really non-trivial stuff. These are annals papers, they're massive. And his asymptotic expansion actually contains constants that depend on T. They don't depend on F, but they depend on T. And this really interferes with my program. They're somehow simple to understand terms, but I haven't understood them yet. He doesn't care about this type of thing. He's more interested in showing that there are non-trivial obstructions to solving the cohomological equation. But as I say, I'm working with a student of Forney named Rodrigo Trevino, and he thinks that we can make this work, maybe not for this case yet, but for some slightly simpler examples involving solenoids. But I'm quite optimistic that there's there's an interesting theorem to be had here. So I'll stop there. Thank you.